Okay, here are the solutions of the homework as a follow-up from lesson 2. In which of the following regions of the electromagnetic spectrum is radiation of wavelength 600 nanometers? This one is visible light. You should know that the visible region is between roughly 400 to 780 nanometers. This is not very accurate. You can look this up if you want. Number 3 is a graph of displacement versus acceleration. We have covered this before. Answer is A, which you should already know. Number 4 is actually an HL question, so standard levels can skip this one. We're given that for a mass attached to a spring has a displacement x and released, so x would be the amplitude, and when that's the case, the period of oscillation is t. For an initial displacement of x over 2, what will be the best estimate for the period and oscillation of the total energy of the system? The answer is B, because like we described before, the displacement, the amplitude doesn't change the period, but total energy is proportional to the square of the amplitude. So square of half would make the total energy a quarter of initial value. Number 5 is about executing simple harmonic motion. The restoring force is always proportional to the displacement that is in the definition. You should already know. Number 7 is another high-level question. We are given an oscillation with period t and looking for the graph of how the kinetic energy varies with time. The energy will be C, because if you start from the amplitude of the motion, the kinetic energy will start from 0. Half a period later, it will reach the other amplitude, so again, kinetic energy 0. 1 full period later, it will have completed 2 cycles, so this will be the kinetic energy graph. Number 8 and 9 relate to these diagrams. 8 is asking for the amplitude. Now, on a longitudinal wave, it's not easy to find amplitude, so we're going to find our way to describe the displacements of these particles. You know, on a longitudinal wave, these particles are oscillating in parallel direction to the wave propagation. If these are the equilibrium positions of the particles, this particle in diagram 2, which is the next instant, is at the same position as it was. This particle is 2 squares to the right of its equilibrium position. This particle is 4 squares to the right of its equilibrium position. This particle is again 2 squares from its equilibrium position, and this one is again at its equilibrium position. If you continue, you will find that the maximum displacement any particle shows is that much. We are given a scale of 5 squares being 1 centimeter. This is 4 squares, which means the amplitude has to be 0.8 centimeters. Related to the same picture, number 9 is asking for the wavelength. We can pick a particle at the center of a compression and look for the next particle at the center of a compression. That gives us the wavelength, which is 8 centimeters. So the answer to number 9 is C. Number 11 gives us a graph of measurements of height over sea level at times in a bay. Which of the following gives the approximate amplitude, the period of the tides? Now, we don't know where exactly the equilibrium position is, but we know from one crest to the next trough that height should be twice the amplitude. So you can estimate that value, and when you calculate that, you're going to find that half of that total distance calculates to about 6.5 meters. That rules out 13, because from here to here it's about 13 meters looking at the graph scale. So half of that will give us the amplitude, and the time period is 12 hours, because from the beginning, from the crest, that's when it reaches its crest again. So you choose the best answer among the options, which is C. Number 13 gives us a wavefront diagram. As explained in the lesson video, the distance between the wavefronts gives us the wavelength. So you have to measure that distance, which is the wavelength. If you use the scale of 1 centimeter, you can find that wavelength is about 1.5 centimeters. We're given the frequency to be 10 hertz. Since speed is frequency times the wavelength, We multiply 10 by 1.5 and we get 15 centimeters per second, which is C. Number 13 is about reflection of a wave. We know in the question that a pulse moves towards a fixed end, so we expect that the reflected pulse must be inverted. It should have less energy, but it cannot move more slowly. The reason it has less energy is that at every boundary there will be some absorption and some transmission, which we will discuss in a later lesson. And it is moving with the same speed because it is in the same medium. That means the answer to 13 is C. In number 15, we're given a pulse that is traveling to the right along a string. In lesson 3, we learned that the particle is moving vertically because this is a transverse wave, and the wave is moving to the right. So in that instant, the P is at that location. In the next instant, since the wave is moving towards the right, that will be the position of particle P. So on a vertical, particle P is here at this instant. Next instant, it's going to be there, which means it is on its way down. Number 16 is about superposition of two waves. We have learned in lesson 4 that when two waves meet at a point in space, that their displacements always add up. You might think the answer is amplitude, but amplitude is only the name given to the value of the maximum displacement. So 17 is another question about superposition. We're looking for the displacement of the resultant wave when they meet at time t. So at time t, the first wave has a displacement of x1, and the second wave has a displacement of negative x2. The sum of those two will give us B. Number 18 is another question about reflection from a fixed end. When the pulse reaches y, it will be inverted and move at the same speed. So it will be reflected and be inverted. So that gives C. Thank you.